I think we're going. All right. So Enrico is a PhD candidate at the University of Strathclyde, Glasgow, and jointly at the and at Quantino. He focuses on near and medium-term algorithms for noisy quantum computers, variational quantum algorithms. He has worked on exploring the noise resilience of VQAs, the noise-induced barren plateau phenomenon, error mitigation techniques, and more recently on the interplay between noise and simulability and Fourier decompositions of VQA optimization landscapes. Let us all welcome our speaker.
Thank you very much. Has the recording started? I do not see.
Yes.
Okay.
It's
awesome. Okay. Thank you very much and welcome to my talk, which will be about classical simulations of noisy VQAs. This was joint work with NPL and Quantinium, and also Manuel, who's from EPFL. So let's start from an overview. In this talk, I will discuss essentially VQAs and how they decompose as a Fourier or trigonometric series, which will then lead me on to the channel mode decomposition that allows to include noise. I will introduce the LOWESA algorithm and explain why we can make efficient simulations of noisy variational quantum circuits. And then I will be discussing briefly about what happens beyond noise. So if you can use these algorithms, perhaps for exact simulations. And yeah, this talk is based on two papers. So the first one is classical simulations of noisy variational quantum circuits. And the second one by Manuel is a classical Fourier simulation of quantum systems with LOWESA that delves a little bit deeper into the noiseless scenario. Okay, so I assume everyone will be familiar with variational quantum algorithms, but I will give a brief introduction anyway. So these are seen as some of the most promising algorithms for the NISQ era, so for noisy quantum computers. And they are roughly based on machine learning algorithms and neural networks, where you have a cost function that encodes the problem, and that is usually obtained from measuring an Hamiltonian, getting the expectation value, and then doing some post-processing. And then this cost function is optimized by a classical optimization loop, as shown in this figure. So yeah, one thing to note is that the Hamiltonian is usually composed of a small number of Pauli measurements or projections. It could also be projections, but usually Pauli measurements. Okay, so why are we doing this? So it can be argued that there are three main motivations. The first one is, of course, it's easy to do this because it doesn't require any fault tolerance. And also we can arrange our circuits to be to fit the native gate set and hardware topology, because we have less constraints on the ansatz and how it should look like. And this was the original reason why people suggested using VQAs. Also, of course, we wouldn't be doing this if it was useless. So there is some hope that we can solve interesting problems like variational quantum eigensolver, which is finding the ground state of, for example, chemical systems. Then you can do perhaps time evolution or optimization using something like QAOA. And yeah, the hope is that VQAs are not classically simulatable, at least not in an easy way. And so they are truly quantum algorithms. And then people conjectured and to some degree observed and proved resilience to quantum noise of VQAs. in some specific settings. And intuitively, this comes from the fact that there is an optimization loop. And so if the parameter space, if the landscape is shifted a bit with respect to parameter space by noise or is somehow modified, the classical optimization loop can still find the minimum, which should correspond to approximately the solution. And also, these algorithms are amenable to quantum error mitigation techniques that have been designed specifically for variational quantum algorithms. However, I want to raise a little bit of a doubt on this last point, because essentially, well, we shouldn't expect noise resilience to hold for all noise and all strength, right? So there must be a regime in which it fails, and the reason is that if you just had maximum noise, of course, your algorithm would be, it would be very bad, and you also should be able to simulate it. So there must be a regime in which, if there is any noise resilience, then it exists there, and outside that regime, it does not. At least that's the hope. But yeah, it's not clear why there should be noise resilience beyond these heuristic arguments that I've just given. So yeah, let's challenge this noise resilience concept a little bit. So yeah, essentially, my very first publication analyzed the landscape of the VQE, a very small VQE model, using some basic noise models and tried to identify the noise resilience. And indeed, we found that there is some noise resilience, but it appears to be for very, very low rates. And also it appeared that noise tended to accumulate. So if you wanted to run larger circuits, you needed less noise. And this obviously makes perfect sense, but you can see that this is somewhat of a problem, because if you run very deep circuits, then you want your noise rates to go down as the circuit gets deeper, essentially. And that is definitely not easy, because we cannot easily control noise rates, and definitely we cannot make them as small as we want. And this was then confirmed to be a very serious problem, known as the noise-induced Barn plateaus. That says essentially that this is a feature of basically any incoherent noise and also measurement noise. And therefore, we're essentially limited in how big of a circuit we can run at a fixed noise rate. And that is both in terms of number of qubits and the number of operations. Okay, let me, for a moment, diverge, or at least seemingly diverge onto the topic of the Fourier decomposition of variational quantum algorithm cost functions. To give you an idea why I'm doing this, this is because it will allow us to understand how the landscape changes with noise, which is what we truly want to do here. So yeah, so essentially it's well known now that variational quantum algorithm cost functions admit a Fourier series representation, which equivalently is also a trigonometric series representation. And this has been rediscovered multiple times in the literature. So yeah, by now it's a very established fact. And essentially what this says is that if you have a circuit with your generators of rotations, then the eigenvalues of these generators will dictate what kind of frequencies you have in the cost function. And so since there is a finite number of rotations, there's also a finite number of frequency modes. Although these frequencies combine together, and so you may end up with a very large spectrum. Oh, sorry, I found out that the text is a bit cut. Anyway, yeah, so, but these works often assume no noise, and so we would like to know how this decomposition of the cost function landscape changes when you add in noise. And the reason is that this is a very nice framework to say something about global characteristics of the landscape, because it allows us to study all the frequencies that compose this cost function. In order to do this, as you might have imagined, it is necessary to move away from the usual pure state picture and then move to channels and density matrices. And so just to give you an overview of what we've done, we decomposed every single poly rotation gate as 3 channels, which are these here. And these channels are Clifford, are linear combination of Cliffords, and they have a very simple form, especially like, as you can see in the bottom here, this is the Pauli transfer matrix notation. So you can understand this as what happens when these channels act on a single poly. And you can see that they act as matrices that are very sparse. And in particular, they always map one poly to another poly. And this is crucial, as we will see very shortly. But in any case, when you do this trigonometric decomposition, you get to the same exact formula that you got to before. However, in this case, you can add in noise very simply. And for example, if you add a poly error right after this rotation gate with some parameters qx, qy, and qz, you'll see that you get now in these D matrices, you'll get some factors that are connected to these poly errors. And so we can directly express the cost function as a trigonometric or Fourier series with these new factors due to the errors. And this leads us to the simulation algorithm, which essentially works like this. And yeah, I'll try to explain it as best as I can, but admittedly, it's a little complicated. So please go read the paper or ask me later if you have questions. So essentially, this is a Heisenberg picture simulation algorithm. And it assumes that your ansatz can be written as uncorrelated single qubit rotation gates, which we can take in general to be Z rotations, preceded or followed by noise channels. And these are polynoise channels, which is a very general type of a noise model. And then all the rest is Clifford gates. So this sounds restrictive, but actually it kind of describes most algorithms that that we could think of. Okay, so now we have this this decomposition of the rotation gates into these Clifford channels. So we see that we can start from the channel, the global channel, which is the parameterized unitary that we're trying to apply, which will be composed of these sequences of Cliffords and rotations. And then if we decompose the rotations into its underlying channels, we get that the cost function becomes a sum over paths, right? Because you can imagine the Pauli operator, which is the measurement that is propagated through the circuit in the Heisenberg picture. And every time it goes through one rotation gate, it can go through one of these channels, right? And so we get a sum of a lot of terms, exponentially many, in fact, depending on the number of gates. And each one of these terms will get a very simple trigonometric factor, which, as you can see here, it's a product of cosines and sines, and so it's a trigonometric monomial. And we also get a factor which is easy to calculate because it's just essentially Clifford channels. And you can always simulate the action of Clifford channels on a Pauli efficiently. And this other bit will also contain the noise information. And in general, without noise, this factor can be 1, -1, or 0. When you add in noise, this will get somewhat contracted. So you get factors that are less than 1. And so you can start to see now that the more rotation gates, noisy rotation gates you put, the more your cost function gets contracted, which is essentially noise-induced Barn plateaus. But even more interestingly, it turns out because each rotation gate is composed, has noise essentially mainly on these bits with the cosine and the sine, that the factors that have the most cosine and sine terms will get dampened more by noise, essentially. And we call the number of cosine and sine terms the weight of this factor. So each term in this summation gets dampened by the noise, roughly, to the power of the weight of the factor. And as you can imagine, this this is very, very crucial because you now have some terms that are falling very, very fast. Okay, so this leads directly to the LOWESA algorithm, which is the low weight efficient simulation algorithm. And the idea is just to repeat this procedure, but to impose a cutoff to the weight. So let me remind you, the weight is the number of trigonometric factors in each monomial, right? So it's every time we go through one of these D gates, if it's either D1 or D -1, we get a trigonometric monomial, we get a noise factor, and we increase the weight by 1. And so we're limiting in this algorithm the number of times that we go through these D1 or D -1 gates. And the reason why we're doing this is that, as you can see, these gates get dampened. So there will be a point in which it doesn't really make sense to explore paths that are longer than some cutoff, because they contribute vanishingly little to the final cost function. Only when noise is present, of course. So the way this algorithm works, you can imagine it as paths, as I said, on some tree. So we picture it like this, and you start from the Pauli observable, and then you go through these branches, and based on the specific Pauli observable, you only have at most 2 choices for which branches to go. And essentially, sometimes the path will exceed the weight cutoff, and then we don't propagate the path anymore. And finally, when the paths get to the state at the beginning, some of those will also annihilate, and we're left only with a few surviving paths that will contribute mostly to the cost function. And so we get our approximation for the cost function as a summation over these paths, weighted by some noise-dependent factor. Okay, so the key result is that, as I hinted, with noise, paths with a large number of rotations are suppressed. And therefore, if we have a noise channel with some known parameters applied after every rotation gate, we can guarantee that the error will be less than this bound, which, as you can see, depends exponentially on the amount of noise and this cutoff L. So if we choose our cutoff reasonably well, we can guarantee that this error will be less than whatever whatever bound we want. Notice that this is a parameter averaged L2 error. So essentially you're integrating the error between the true noisy cost function and the output of LOWESA over the entire parameter space. So there may be points in which this error is larger, but overall, across the whole parameter space, the error is quite small. And yeah, the thing to note is that the algorithm's worst case runtime is polynomial, both in the number of qubits and in the number of rotation gates. It is obviously exponential in L, because otherwise we could just simulate everything by taking L to be large. However, L, again, is a fixed parameter of the algorithm. And so we can set our L at the beginning, and then the algorithm's runtime will always be polynomial. Yeah, so LOWESA, we can see that returns an approximation for the cost function in polynomial time in the number of qubits and gates that is provably accurate within some bounded error that we can control. Of course, there is a trade-off between the time and the accuracy. So if we choose a larger L, we'll get a more accurate approximation. However, essentially the exponent of your runtime will scale, and this can scale very badly. So it's definitely not perfect, but it proves what we wanted to prove, essentially, that you can simulate these noisy variational quantum circuits efficiently. Okay, so let's have a look at some plots. We tested this algorithm on some quite large noisy systems. And in this case, we chose just a simple VQE type of circuit with a connectivity that is expected not to be simulatable by MPS. And this is quite large, so it cannot be simulated by just state vector methods, because as you can see, it goes up to 50 qubits. So on the left, you can see this is the number of paths that should be expected. And as you can see, it grows very, very rapidly with L, because there's a lot of branching, essentially. And so even at L equals 16, you get into some astronomical number of paths. However, if you do your algorithm right, this will actually not have that big of an impact, because there's a lot of paths that essentially die early. And so you can eliminate those and proceed to the other ones. And so we can see that the runtime, even with 50 qubits, is in the order of seconds. And this is with the largest L of 16, which is quite good. And the most important plot is probably the one on the right that shows the error and how so that's the error of approximating the cost function, and how that scales with the noise rate for different for different cutoff values. So the dotted lines here are the theoretical bound that I showed you previously, and then the other lines, the one with the dots, are the experimental values, and you can see that the bound is indeed respected, and actually it looks like it's very loose, at least for low noise rates. Yeah, but as you can see, there is quite a strong dependence on the noise level, meaning that if we go to very low noise levels, the error will become quite high, no matter if we have very large L's. And this is to be expected, because the optimal L, given a certain amount of allowed error, scales like the inverse of the noise rate. So if we cut the noise rate by 10, we have to increase L by 10. But remember that L determines the scaling of the algorithm, and it's exponential in L, actually. It goes like roughly like 2 to the L. And so 10 times bigger L is a very, very, very slow algorithm. Yeah, so there is this characteristic which the algorithm is basically very, very sensitive to the noise rate. But this is to be expected because you do not expect to go to very, 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 very small noise rates and retain some good accuracy, because that would mean essentially simulating an almost perfect calculation. So we're not claiming that you can simulate arbitrarily small noise rates efficiently. However, we should note that it is still polynomial. So even if we go to very, very large L's, it's still polynomial. So in a sense, exponential advantage is completely ruined by even a little bit of noise. Okay, so this slide is from a presentation by Manuel, and you can see it's very nice. There's a very nice GIF, so yeah, I really had to include it. So this is a bit of a detour, and it's about using LOWESA to simulate clean qubits instead. In particular here, this is the famous IBM practical quantum advantage claim that got simulated by multiple teams very shortly after. And also, yeah, so we wanted to join in on the fun, and we tried to use LOWESA to simulate this circuit, which is quite big. So yeah, it may appear a bit strange that we're using this algorithm that was thought to only apply to noisy systems to simulate something that's assumed to be clean, because here they use error mitigation. And the reason is that Manuel had the intuition that maybe you could use LOWESA as a simulation algorithm just for clean systems. And this intuition turned out to be correct, because as you can see, there is a very, very close match between the output of LOWESA and these error mitigated results, and also other results by other teams. So yeah, why this is true, we are not really sure, but the intuition is, I guess, that LOWESA captures essentially the terms of the cost function that are lowest weight. So it seems that in a sense, even on the clean cost function, only the low weight terms, so the ones with few trigonometric components, that these dominate even the clean cost function. For example, we can see that in this depth 6 case, LOWESA can simulate the true output with just a single path, which has weight 34. So it seems that these paths are somewhat sparse, and at least the ones that make it to the end. And it also seems that only the low weight ones, essentially they dominate in the end. And yeah, this is still work in progress, so I can't claim any theoretical result here, but it does make for very nice plots. Also note that one of the powers of LOWESA is over these other simulation algorithms is that we simulate the entire cost function. So we can make these plots, and these lines here, they're not fits, they're the actual output of LOWESA as a function of the parameters, and that means we can also make these very nice animations. For example, this is a time evolution of some, you basically have the system and you initialize it with some of the spins rotated, and then you let it evolve in time. And we can do this very nice visualization because we have full control of how the cost function, which is yeah, this I think here is a single Pauli of how the cost function varies with time. All right, so let me summarize what we talked about today. We proved that under a reasonable and realistic noise model, which is polynoise, many variational quantum algorithms are classically simulatable in polynomial time using this algorithm that we call LOWESA. Therefore, noise, we see that it's a fundamental barrier to exponential quantum advantage, because if you have even little noise, technically, LOWESA simulates your variational quantum algorithm with polynomial time, although the exponent may be very, very large, so it may not be practical. However, if the hardware noise is sufficiently large, LOWESA may be actually be more practical, because it may be more accurate and it's definitely more efficient than running on a quantum computer, because you can run it on a laptop, for example. And there are indications also that LOWESA has a role as a standalone simulation algorithm. As we saw in the previous slide, we still do not understand theoretically why this is true, but I guess the same can be said of many other simulation algorithms. And it seems like LOWESA has a niche in scanning phase diagrams, for example. As we saw in the previous slide, you can see how exactly some observable changes as you change, for example, time or I don't know, magnetic bias or something like that. And therefore, we have control over the VQA cost function, so it can be used to do some meta learning on these cost functions, because you can just simulate a lot of these cost functions very cheaply, and then yeah, and you can also optimize VQAs on a classical computer, for example. So to note, LOWESA cannot do sampling. So if, for example, you have some algorithm that requires you to first optimize and then sample, like, for example, a generative modeling algorithm, you can do the optimization stage directly on the classical computer. And then you can use the quantum computer to sample. So you can do a lot of new algorithms and new ways to approach variational quantum algorithms. And yes, there's also some caveats to this. So I kind of swept it under the rug, but LOWESA only works for uncorrelated single qubit rotations only. So for now, things like QAOA or HVA that have large blocks of correlated rotations, they are not approachable by LOWESA. By correlated, I mean that the angles of these rotations are correlated. So yeah, I should note that LOWESA actually works, so the algorithm works, but we cannot guarantee that the bound is respected. So that's the issue. It's a bit of a technicality, but yeah, maybe there's something deeper at play here. Also, as I hinted, there is a very large exponent of this runtime with realistic noise levels. So maybe this is this algorithm may not be practical going into the future. And also, we're only doing expectation values and not sampling. So finally, I want to pose a few open questions that would be interesting to know. The first obvious one is, can we actually extend it to these other circuit structures, like a QAOA or HVA with correlated angles? And if not, why? What is special about these correlated settings? So yeah, there's also a few other technical questions, like the bounds are quite loose. Can we characterize the average case behavior? Can we say something about how this behaves in some subsets, some specific problem instances? And also, crucially, I would like to know why it works so well for the noiseless setting, because this seems to say something about the cost function of these algorithms. It seems to imply that it's dominated by low frequency components. And that sort of makes sense, but I would like a very theoretical understanding. And yeah, finally, it would be personally interesting to extend LOWESA to incorporate symmetries, which is related to the QAOA or HVA question. But yeah, I guess it's a little bit more general. So there are some algorithms with symmetric structures, and we would like to see if LOWESA applies here, perhaps with some modifications. So perhaps it's not a trigonometric series anymore, could be something else. I don't know. It's quite difficult to understand these regimes, but hopefully we'll get there. So yeah, this is the end of my presentation. So I would like to thank you for listening, and please ask me any questions. I'm happy to answer them.
Okay, thank you for the very nice talk. So as he said, we open for questions now. Does the audience has any?
Hi, thank you for the nice talk. I would just want to ask, probably I'm not sure if I understand correctly. You classically simulate the VQE algorithm, and the way you do it is that you like decompose the cost function into some trigonometric function, and then you convert them into some graph, and you cut some longer path you don't want. Is that correct? I mean, you have to design the graph for specific problem each time for the specific circuit, right?
Oh, yeah, that is a very good question, actually. So yes, that is roughly how the algorithm works, is you construct this graph, and then you explore these paths. So the graph is a tree, and some of these paths are they're interrupted either because they annihilate or they go over this cutoff. However, a very important thing that actually you just made me realize that I did not say, and that was very important, is that this graph is fixed for any parameter initialization, and it only depends on the circuit structure, right? So if you take a look just at the ansatz without any parameters being set, you can directly infer the graph. And so yeah, so once you compute the graph once and the path once, you can you have an algorithm that is valid for any parameter initialization. And yeah, this is actually a very good point, because this is one of the strengths of the algorithm. So basically, calculating these paths, it can be costly, especially if you go to very, very large L's, because you have a potentially enormous number of paths. However, once you do this calculation once, and you can do it on a supercomputer, you can do it on a GPU because it's highly parallelizable. And once you do it once, you have the cost function, and you can train your model, you can do whatever you want with very, very little computational cost, because it's just a function, right? And you can calculate it with a laptop or whatever. And so this is actually how Manuel generated all those nice plots. He got the cost function with the parameters essentially being floating first on a very large computer, I think actually a supercomputer. And then he evaluated these paths for like specific parameters on a laptop. So all the post-processing can be done very cheaply. So yeah, no, that's an excellent question, actually. Thanks for asking.
Okay, thank you for the answering. I just want to verify. So different ansatz have different graph, right?
Yes.
Okay, and is it cost to have the initial graph construction? You say if once it's done is cheap, but is the construction of the graph costly?
Yeah, it is costly, and that's the exponential factor that I talked about before. So the runtime that I gave was essentially the runtime to construct the whole graph. So when I said the algorithm is polynomial in number of qubits and gates, but exponential in the cutoff, I meant really about the graph construction. I wasn't even including the evaluation of the cost function because that is just so cheap that essentially it doesn't matter. So yeah, no, it can be costly. However, in principle how costly it will be based on how many rotation gates and what parameter you choose. So it cannot be arbitrarily costly, let's say, because your graph has some characteristics that are known. And for example, as I mentioned, you can only split every branch at most into 2 other branches. Yeah, okay, so there's another thing that maybe I should say is that the graph changes based on the Pauli operator. So yeah, there is a possible caveat, is that you have to calculate one different graph for every Pauli operator. So really this algorithm is efficient only if you're measuring Pauli operators. Sorry, if you're Hamiltonian that you're measuring is decomposed in a polynomial amount of Pauli operators. But that is often the case because that's what you're really also doing on the quantum computer. You're measuring these same Paulis. So you do not want an Hamiltonian that has an exponential number of Paulis. And the exception, of course, is projective measurements. And that is the reason also why LOWESA cannot simulate sampling, for example, is that you cannot really do projective measurements because they have exponentially big number of Pauli operators, at least at the moment. So yeah, I hope that answers your question.
Yeah, yes, it's good. So a further question is, usually we don't know what's the best ansatz to simulate the system. Usually we have to design the ansatz. But according to what you say, once you have the ansatz, you can efficiently simulate them. So do you prefer the strategy to construct very complicated ansatz and do the classical simulation, or you try many ansatz and construct the graph independently and see what's the best results if we have this simulable algorithm? So what's the strategy you think is best?
So, okay. So it really depends because I haven't really explored the inverse problem of given a graph, constructing an ansatz that does it. But I don't feel that will be very complicated, so probably you can do it. I guess it depends on your settings. So, for example, if you want to generate, like, why would you want to start from a cost function and then construct an ansatz? Well, maybe in a setting where you're trying to do some, cost function fitting or something like that. Maybe you're required to have a certain number of frequencies, and then maybe that informs your ansatz construction. However, in general settings, I would say you start from an ansatz usually, and then you look at the graph and then you use it to simulate it, right? So in general, you have some rules and some logic to construct a specific ansatz in a certain way. And, there's a ton of literature on that, and I'm by far not an expert. So yeah, I understand usually it's one way more than the other. However, I should add that these kind of results, they also tell you that some ansatzes are more easily classically simulatable than others. So perhaps maybe you can use these results to construct ansatz that are adversarially hard for LOWESA to simulate. And these would be, for example, these correlated parameter ansatzes, right? So there's this indication that the error of LOWESA may be very bad for these correlated parameters. And essentially the reason seems to be that these correlated parameter ansatzes, they have a lot of very high frequencies, but not a lot of low frequencies. And since LOWESA starts from the low frequencies and goes up, you may never get to the high frequencies. So the error may be arbitrarily large. So there is this indication that these algorithms with correlated angles that give very high frequency landscapes, these seem to be the ones that are harder to simulate. And so in a way, maybe, I don't think this helps you that much in ansatz design for like problem-specific ansatz design, but it probably helps you to create ansatzes that are hard to simulate, or that, you know, we can hope to have some quantum advantage. So yeah, I see it more that way, but yeah, I do not exclude that these algorithms could be used for ansatz design. It's just a question I haven't explored myself personally. I think Manuel is a bit more interested in that side, so perhaps he will publish something. I don't know. But yeah, it's definitely an open question. Yeah, I mean, I would be very happy if one of you try to to use this for ansatz design, because it's definitely very interesting.
Yeah,
so yeah.
thanks. Yeah, thank you for the answering. It is also helpful. And another question is, so is the noise model you are using? So I mean, is the algorithm limit to certain noise model? I mean, it can it be more general, or if it's not that specific, the simulation result will be different?
Right. That's a very good question. So we have explored other noise models, but they were still polynoise, single qubit polynoise. So the question of what noise model accurately reflects quantum computers is very complicated. There's a lot of work in this direction. From what I understand, it is roughly accurate to have depolarizing, single qubit depolarizing noise. Like from what I understand, that describes a lot of the noise that you see. Now, people try to make very, very refined noise models, and these usually end up having also some multi-qubit noise models, also non-unital noise, like amplitude damping, things like that. Those are harder to describe in LOWESA. It's not impossible because the framework is very general, but yeah, the results will not look that nice. So the reason why I don't think that's a very big issue is that, again, these noise models are usually included on top of single qubit polynoise, because single qubit polynoise is by far the easiest one to characterize because you can do randomized benchmarking and all of that stuff. And we know it's always present, essentially. So yeah, so I think the results are valid for real quantum computers as well, because I don't think you can ever, at least without error correction, get rid of this single qubit polynoise. So yeah, it's a great question, but like my hope is that these results are very general, and I have indications that that is true. However, the topic of noise modeling is quite complicated. I am definitely not up to date. So yeah, I cannot guarantee that this will be fully accurate, but to the best of my knowledge, this is a good noise model. Yeah.
Yeah, thank you. I agree. This is a good noise model to this study for the case. And my final question is more general. Like in the classical simulable approach, what's the goal? I mean, if we can simulate these classically efficiently, does it mean that finally the quantum computer is not that as powerful as we like? Do they show the advantage? So what's the implication? I mean, if you can really classically simulate them.
Okay. So I guess the result was interesting per se, that because previously nobody had really shown that the exponential advantage was not possible for these circuits in this setting and with noise. So I guess from a purely complexity theory point of view, this is a useful result, perhaps. Although I'm not a complexity theorist, please don't ask me questions. I would struggle very much. But yeah, so from what I understand of these results, the implications are, at least at the start, in my mind, the implications were more theoretical. Because yeah, you can simulate these things polynomially, but the exponent may be so large that in practice, you still have a quantum advantage. It's just no longer an exponential quantum advantage. However, recently, and this is mostly Manuel's work, and I need to thank him for that. Recently, this algorithm has taken a life of its own as an exact simulation algorithm. So that leads me to think that perhaps these models, they are naturally simulatable by something like LOWESA to a very good accuracy, even without noise. So yeah, that would have big implications, because that would essentially mean that at least these uncorrelated ansatz, they're not good. Like we cannot use them essentially, or at least we can use them, but we cannot argue that they're a quantum advantage or anything like that. But that still remains to be shown. So I see this as a first step in showing that perhaps variational quantum algorithms are they can be dequantized essentially. Although I do not expect all variational algorithms to be fully dequantized, but this is an indication that at least some of them can. So we need to be careful when we make quantum advantage claims, like IBM, but I don't want to point fingers. But whenever everyone makes quantum advantage claims, we need to be really careful with these variational quantum algorithms because yeah, there's a lot of good simulation methods, and this is just one of them. So yeah, I hope that answers your question.
Yeah, thank you. So yeah, it's very good. I think this is a very good work, and you have give a nice presentation and answer my questions. So thank you very much. It's good. Thanks.
Thank you. Those were excellent questions, I have to say. Yeah, thank you very much.
Thank you.
Okay, I think our time is almost up. So perhaps we can have time for one last question. if there's any.
I have some time. I'm not going anywhere, so. But
Let's see it.
yeah.
Okay, perhaps that's for now.
All right.
So I would like to thank you again for accepting coming here and give us a nice talk. And let me stop the recording.
Okay, thank you very much.
Thank you. Since you stopped the recording, I have more personal question.